In this video, I'm going to show you how to solve problems associated with the Carnot engine. And then towards the end of this video, I'm going to talk about the Carnot cycle and all the steps that are associated with it. So let's go over this problem first. Calculate the maximum efficiency of a heat engine with operating temperatures of 300 Celsius and 500 Celsius. The maximum efficiency that a heat engine can have is known as also the Carnot efficiency. And so to calculate it, we can use this equation. So the efficiency of a Carnot engine, or an idealized heat engine, that's the best that a heat engine can be, it's 1 minus Tc divided by Th, where this represents temperature values in Kelvin. So Tc is currently 300 Celsius. So we need to add 273 Kelvin to that. So this is going to be equal to 573 Kelvin. And Th, the hot temperature, is 500 Celsius. So if we add 500 plus 273, this is going to equal 773 Kelvin. Now let's plug it into this formula. So Tc is 573, Th is 773. So this works out to be 0.26 as a decimal. So to convert it to a percentage, multiply by 100%. So the efficiency of the Carnot engine is 26%. So that's the maximum efficiency that this heat engine can have given these operating temperatures. Number 2, a Carnot engine is operating at temperatures of 400 Kelvin and 700 Kelvin. If 14,000 joules of heat energy is absorbed by the engine, how much heat energy is discarded into the cold reservoir? So let's draw a picture. So that's the engine, and this is going to be the hot temperature reservoir, and this is the cold temperature reservoir. So the temperature is 700 Kelvin. So that's Th. And at the cold reservoir, it's 400 Kelvin. And so that is Tc. And so this is the engine itself. And we know 14,000 joules of energy is being absorbed by the hot temperature reservoir. So that's equal to QH. Our goal is to calculate QC, how much energy is going into the cold reservoir. And the formula that we can use to get this answer is this equation. Th divided by Tc is equal to the absolute value of QH divided by the absolute value of QC. Now in this example, Th is 700 Kelvin and Tc is 400 Kelvin. QH is 14,000 joules. Now QC technically is a negative number, but let's get the absolute value of QC for now. So let's cross multiply. So this is going to be 400 times 14,000, which is a big number. That's 5,600,000. And then 700 times QC. So QC is 8,000 joules. At least that's the absolute value of QC. QC itself is negative 8,000 joules because heat energy is being released from the heat engine into the environment. And so that's why it's negative. So that's it for part A. So we have the heat energy being discarded into the cold reservoir. Now how much mechanical work is performed by this engine? The mechanical work is the difference between QH and QC. So we have 14,000 joules of heat energy entering the engine, and 8,000 joules of heat energy leaves the engine. That means that 6,000 has to go this way. And so that's the mechanical work. So it's 6,000 joules per cycle. Now let's calculate the efficiency of the Carnot engine. So I'm going to use a different variant of the equation that I used last time. So it's equal to Th minus Tc divided by Th. And this, of course, has to be in Kelvin. So Th is 700 Kelvin, Tc is 400 Kelvin, divided by Th. So 700 minus 400 is 300. So it's 300 divided by 700, and so the efficiency is 42.9%. But as a decimal, it's 0.429 or 0.42857 if you want a more exact answer. So you just need to take this value, multiply by 100, and then you can get this rounded answer of 42.9%. So that's the maximum efficiency of this particular heat engine. Number 3, 7,500 joules of heat energy is absorbed by a heat engine from the hot reservoir at 600 Kelvin, and 6,000 joules is released into the cold reservoir at 300 Kelvin. How much work is performed by this heat engine? So you can draw a similar picture as what we did in the last problem, but I'm going to write down the values that we know. So Th, the hot temperature, that's going to be 600 Kelvin, and Tc is 300 Kelvin. Now QH in this example is 7,500 joules, and QC is 6,000 joules. Keep in mind, QH divided by QC, the absolute value, is only equal to TH over TC for a Carnot engine. That's for an ideal engine. We don't have an ideal engine in this example. So for this regular heat engine, this ratio will not work. Now let's work on part A. How much work is performed by this heat engine? So the work is the difference between QH and the absolute value of QC, which we have those values. So that's going to be 7,500 minus 6,000. So W in this example is 1,500 joules. And so that's the answer for part A. Now, part B. Calculate the efficiency of this heat engine. Not the ideal efficiency, but the regular efficiency. So that's going to be the work of the engine divided by QH multiplied by 100%. So the mechanical work is 1,500 joules. QH is 7,500 joules times 100%. So 1,500 divided by 7,500, that's 0.2 times 100%. So the efficiency of the heat engine is 20%. Now, what is the ideal efficiency? What is the maximum efficiency of the heat engine, or basically of a Carnot engine with these operating temperatures? So the formula that we're going to use is this equation. It's going to be 1 minus Tc divided by Th. So this is going to be 1 minus 300 Kelvin, that's Tc, and Th is 600 Kelvin. 300 divided by 600 is 0.5, and 1 minus 0.5 is 0.5. So the efficiency is 0.5, and if we multiply that by 100%, it's 50%. So right now, this particular heat engine is not doing too good. It's 20%. So we can probably improve this heat engine, but the maximum efficiency that we can attain is 50%. That's the ideal, given the operating temperatures that we're dealing with. Number 4. A heat engine releases heat into the cold reservoir at 500 Kelvin with a Carnot efficiency of 25%. What exhaust temperature will increase the Carnot efficiency to 60%? Well, let's write down the information that we know. So right now, the efficiency is 25% or 0.25 when the exhaust temperature, the cold temperature, is 500 Kelvin. What we don't know is the hot temperature. Now, we want to increase the efficiency to 60%. And so we need to change the temperature of the cold reservoir, which is the exhaust temperature. Now we're assuming that the temperature of the hot reservoir is constant because nothing was specified regarding it. So let's calculate TH for the first situation. So let's start with this formula. E is equal to 1 minus Tc divided by Th. So I'm going to take this and move it to that side. And so Tc over Th is equal to 1. And then I'm going to take this term, move it to that side where it's going to become negative E. On the left, it's positive E. So Tc over Th is 1 minus E. Now let's multiply both sides by Th. So on the left, these will cancel. So I just have Tc on the left. On the right side, it's Th times 1 minus E. So now let's calculate Th. Tc is 500 Kelvin, and the efficiency is 0.25 for the first situation. Now 1 minus 0.25 is 0.75. Now let's divide both sides by 0.75. 500 divided by 0.75 gives us a temperature of 666.7 Kelvin. So now, for the second situation, we're going to assume that this temperature is the same, it doesn't change. Let's calculate the new cold temperature using this formula again. So Tc is equal to Th times 1 minus E. So Th is 666.7 Kelvin, and the efficiency is 0.6. So 1 minus 0.6 is 0.4. So we need to multiply 666.7 times 0.4. And so that's going to be 266.7 Kelvin. So now let's talk about what's going on here. As the temperature of the cold reservoir decreases from 500 Kelvin to 266.7 Kelvin, the efficiency decreases, actually it increases rather, from 0.25 to 0.60. So this means that if we decrease the temperature of the cold reservoir, the efficiency increases, an increase from 25% to 60%. So these two are inversely related. And it makes sense because if we look at this formula, Tc is in the numerator of the fraction. And if you decrease the numerator, you decrease the value of this fraction. And so 1 minus that fraction would actually increase the efficiency. Now, the second way to change the efficiency of a Carnot engine is to affect the temperature of the hot reservoir. So if we decrease the temperature of the cold reservoir and the efficiency goes up, in order to increase the efficiency, we have to increase the temperature of the hot reservoir. If we do that, the value of this fraction decreases. And so it's not going to decrease this number as much. So by increasing the hot temperature, or the temperature of the hot reservoir, you can increase the efficiency. Or you can do it by decreasing the temperature of the cold reservoir. Now let's talk about the Carnot cycle. So what we're going to do is draw a PV diagram. And so we're going to put pressure on the y-axis, volume on the x-axis. And so there's 4 steps. The first step is an isothermal expansion. The second step is an adiabatic expansion. And then we have an isothermal compression, and then an adiabatic compression. So let's call this A, B, C, and D. So for step 1, we said we have an isothermal expansion. And so this is going from A to B. That's the first step. And during the isothermal expansion, heat energy goes from the hot reservoir to the heat engine. So the system absorbs heat energy during this process. Now, during an isothermal process, the change in temperature is 0. So the change in the internal energy of the system will be 0 as well. Now, delta U is equal to Q minus W. So if delta U is 0, Q is equal to W. Now QH, which is equal to the work going from A to B, you can calculate it using this formula. It's nRT, where T is the temperature of the hot reservoir, multiplied by ln V final over V initial. Now, since we're going from A to B, V final is the volume at B, V initial is the volume at A. So that's how you can calculate QH in this example. Now, it's important to understand that the work done for any expansion is always positive, and for a compression is negative. So from A to B, we have an isothermal expansion, so the work done by the gas is positive. Now let's move on to the next step. Let's focus on B to C. So going from B to C, what we have is an adiabatic expansion. Now, because the gas expands during this process, W is still positive. Now, for any adiabatic process, Q is 0. So no heat energy flows from B to C. So keep that in mind. That's very important to understand. Now, delta U is Q minus W. So if Q is equal to 0, the change in the internal energy of the system is equal to negative W. So W is equal to negative delta U. Now, the change in the internal energy is NCV delta T. So to calculate the work done going from B to C, you can use this formula. It's negative NCV delta T. Now, keep in mind, CV is dependent on the gas that you're dealing with. So for a monoatomic gas like helium, neon, argon, these are gases where each particle only contains one atom. CV is equal to 3 over 2 times R. And R is 8.3145 joules per mole per Kelvin. Now for diatomic gases like N2, H2, O2, these are molecules with 2 atoms per particle. CV is equal to 5 over 2 times R. Now let's move on to the next part, going from C to D. So in this part, we have an isothermal compression. Now for any compression, anytime the volume decreases, the work done by the gas is negative. So work is being done on the gas. When the work is positive, work is being done by the gas. Now, because we're still dealing with an isothermal process, the temperature is constant. So the change in temperature is still 0, and therefore the change in the internal energy of the system is also 0. So Q is still equal to W. So QC, we're dealing with a lower temperature now. At this point, this is the higher temperature, and this here is the lower temperature. So at QC, that's equal to the work going from C to D. And QC is going to equal nRTC, the cold temperature, times the natural log of the final volume divided by initial volume. Since we're going from C to D, the final volume is VD, the initial volume is VC. And from C to D, heat energy is being released from the heat engine into the cold reservoir. Now let's focus on the last part, going from D to A. So what we have here is an adiabatic compression. And so the work done for that part, let's see if I can fit it in here, is negative as well. Now for any adiabatic process, Q is still 0. And since delta U is Q minus W, delta U is negative W. So the work is going to equal negative NCV delta T. And this is going from D to A. So now you can calculate the work for each step in this process. Now if you want to calculate the net work done for an entire cycle, it's simply equal to the area under the curve. Now it might be difficult to calculate the area of that curve. However, a simpler way is to use this formula. W is equal to QH minus QC. And so I'm going to stop it here. And that's the end of this video. So thanks again for watching this video, and have a good day.